Multiplication can be thought of as repeated addition, or it could be thought of as a shortcut to repeated addition. Take a look at this pattern. We have 7 plus 7 plus 7 plus 7. 7 is being used as an addend 4 times. So we can actually find the answer here by multiplying 4 times 7. So 7 used as an addend 4 times means 4 times 7. Now 4 and the 7 are called factors in this process, and we know that the answer here, 4 times 7, is 28, and that answer 28 is called the product. So the items being multiplied are factors. The answer in the multiplication process is called the product. There are several ways to indicate multiplication. I'm using the arithmetic version here, the little X to indicate multiplying here. A dot can be used, or parenthesis. All mean the same thing. It means to multiply these factors. Let's go through the process. You recall from earlier arithmetic probably that when multiplying a couple of 2-digit numbers like these, we would arrange them like this. It's the same arrangement that we used in adding and subtracting. That is, the arrangement is to align the 1's digits with one another and the 10's digits and so on if we have other digits. And then when we multiply these sort of separately. That is, we multiply 3 times 47 and put the result down here, and then 2 times 47, put the result down here, and then add some digits. Let's go through the process. 3 times 7 is 21. I'll write the 1 and carry the 2. 3 times 4, 12, and 2, 14. So I'm writing 141. All this means is that 3 times 47 is 141 ones. You see, I mean, that is a way to think about it. And then 2 times 47. Now notice that we're multiplying a number which is in the 10's digit. So when we get a result here, we have so many 10's. And the 10's digit is right here. And that's why the last digit in this group of digits ends right here. And that's why when we multiply 2 times 7 to get 14, we put the 4 here and carry the 1. Let's see, 2 times 7, 14, I'm carrying 1. 2 times 4, 8, and 1, 9. And now we draw the line and add 1, 4 and 4, 8, 9 and 1, 10. So we have 1,081 for this product. Here's one that's a bit more imposing, 439 times 207. We would set it up like this for multiplication. And when the numbers get a little bit large like this, we might want to estimate the answer to verify that we're getting something that sounds reasonable. Well, let's do that here. To go through the estimate, we would round this to the nearest hundred. It becomes 400. Rounding this to the nearest hundred, it's 200. Now, let's go through the multiplication process. We have, let's see, 0 times these 3 digits would give these zeros. 0 times these, zeros. 2 times 0, 0. 2 times 0, 0. 2 times 4, 8. There must be a shorter way. But when we add here, we get 80,000. But there's a shortcut to this. I mean, notice that up here, that when we perform this multiplication, and we have 0 times these digits, we're going to get just a bunch of zeros here. And the stair-step idea, the stair-step form down here is just designed to put digits of the same value, of the appropriate value, under one another. And so all we need to do is just slide over, and when we multiply this digit times those digits up here, just put the first one to the right here. You see, rather than have to make a row of zeros. And we can use the same technique twice here. It's 0 times these rascals is 0, 0 times these, 0. So those are just placeholders. And now 2 times 0 is 0, 2 times 0 is 0, 2 times 4, 8. And we get the 80,000 that we expected. Now another technique is to notice that we have 4 zeros here in 80,000. And we have 4 zeros over here. You see, so really all we had to do was multiply the important digits 2 and 4. See, 2 times 4, 8, and then attach 4 zeros, and we'll have our answer 80,000. So there are a lot of ways to deal with this. All right, now also let's notice that in making this estimate, we rounded 439 down to 400. We rounded 206 down to 200. So we rounded both of these numbers down to other values. So it should make some sense that our answer over here is going to be bigger than, greater than this answer over here, this estimate. Might be quite a bit greater, it turns out. Well, let's see what the result is. 6 times 9 is 54. I write the 4 and carry 5. 6 times 3 is 18, and 5 is 23. Write the 3 and carry the 2. 6 times 4 is 24, and 2 is 26. Now, 0 times this whole row. See, we can use the technique we talked about over here. 0 times all of these rascals is just going to be a bunch of zeros. I'll just put the first 0 as a placeholder and now go on about the business of 2 times all of these, and I'll put begin my result of that down right here. So 2 times 9, 18. Write the 8, carry the 1. 2 times 3 is 6, 1 is 7. Then 2 times 4, 8. And now adding, I get 4, 3 and 0, 3, 6 and 8, 14, carrying the, write the 4, carry the 1, 1 and 2, 3 and 7, 10. Put down the 0, carry the 1, 1 and 8, 9. So 90,434, a good bit bigger than 80,000, but that's kind of what we expected. There are a number of ways of indicating multiplication, number of words or word phrases that lead to multiplication. The word times, it's pretty obvious, leads to multiplication. 7 times 3 means to multiply those two factors. The product of, you see, the product of leads to multiplication because the word product means the answer in a multiplication, in the multiplication process. So it's no wonder then that when we say the product of one thing and another, all we're doing is identifying the factors involved in the process of multiplication. So the product of 7 and 3 means that 7 and 3 are factors, and we perform the operation to find that product. All right, 7 multiplied by 3, that also means 7 times 3. So a lot of ways to indicate multiplication. Here's another situation involving multiplication. It also involves evaluating. Suppose we want to evaluate 2xy, and we're given the value of x and y. Now notice the structure of this, 2xy. It means 2 times x times y. It means that these three numbers are to be multiplied. Now x and y are variables here. And we're given their value down here. But this means to multiply these three factors, even though there is no multiplication symbol that's used here. Those symbols don't need to be there when we're talking about letters. Okay, to evaluate, we would write the expression and then replace letters with numbers. I'll bring down the 2. Now to write the x value is 5. Do I write 2, 5? No. If I write 2, 5, that's 25. So I have to indicate somehow that we're multiplying those two. So I have to introduce a multiplication symbol. I can use the dot, I could use the little x, or I could use parentheses. So 2 times 5, and then the y value is 7, and away we go. 2 times 5, 10. 10 times 7 is 70 for the value of this expression when x and y have those particular values. As you might imagine, there are properties associated with multiplication. And you know, you may have noticed that we didn't talk about properties of subtraction. And one reason for that is that subtraction is related in a particular way to addition. And so it is thought that you don't need properties. But I mean, if you think about properties like the commutative property of subtraction, gee, would that hold here for whole numbers? That is, you remember commutative means that we can change the order involved in the operation. So let's see, 5 minus 2, would that be the same thing as 2 minus 5? No, not the same thing. So there is no commutative property for subtraction. But there is a commutative property for multiplication because we know that 3 times 5 has the same value as 5 times 3. It's 15 in either case. So we can change the order of items being multiplied. To generalize the situation, we would say that if A and B are any old ordinary everyday household whole numbers, then A times B is equal to B times A. Also, the associative property holds. That is, we can regroup in this idea of multiplication. When we're multiplying 3 items, we can multiply the first 2 of those 3 first and then times the other one, or we can multiply the last 2 and then multiply times the first. Now notice the indicator here, the dot and the parenthesis. That's a little bit redundant. We don't really need to do it that way, but just for emphasis here and to show that all we're doing is changing the association or the grouping from these 2 factors to the last 2 factors. We're kind of using that kind of redundant kind of notation. And to generalize the situation, A times B times C, if we're multiplying any three whole numbers, we can either multiply the first two or the last two first. A couple of other properties. There's a multiplication property of 1. And we know that when we multiply any whole number times 1, we get the whole number we started with. That is, 5 times 1 is equal to 5. And sometimes 1 is called the identity element for multiplication because we're maintaining the identity of the whole number we start with under this operation of multiplying. And to generalize the situation, it's A times 1 is equal to A. Another property is the multiplication property of 0. And it goes like this, that when we multiply, and 0 is one of the factors, then 0 turns out to be the product or the result of that multiplication. Now, if we had a whole string of factors here, we could have 10 factors listed here, and if just one of them is a 0, it turns out that the entire product is 0. A discussion of exponents can actually start with a discussion of adding and multiplying. Here we see that 5 is added 4 times. So we say that we have 4 times 5, and we write 4 times 5 like this. So in this way, repeated addition leads to multiplication. Now, it'll turn out that multiplication will lead to the idea of exponent. Here we have 3 times 3 times 3 times 3, or we say that 3 is used as a factor 4 times. So we have 4 factors of 3. 4 factors of 3. Now this leads to the notion of exponent. We can write this situation, the notation for it is like this. We write a 3 with a little raised 4. And in this situation, the 3 is called the base of the exponent, and 4 is called the exponent. The exponent simply tells us the number of times that the base is used as a factor. So the exponent 4 says we have 4 factors of 3. And we read this 3 to the 4th power. Here's another example. Now notice how many factors of 7 we have. There are 5 factors of 7. So in exponent notation, we'll write 7 as the base and 5 as the exponent. And we'll read this 7 to the 5th power. There are two situations that kind of have special names. Here we have 2 factors of 5. So 5 is the base, 2 is the exponent. Now we could read this as 5 to the 2nd power, but generally when 2 is used as an exponent, we can read it as 5 squared. So squared when 2 is used as an exponent. Here's another situation that has kind of a special exponent. Here we have 3 factors of 4. So 4 is the base, 3 is the exponent. This is read 4 cubed. Now it could be read 4 to the 3rd power, but often it's read 4 cubed. Take a look at this pattern involving exponents on 10. We have 10 to the 1 power is equal to 10 because this is just one factor of 10. And by the way, factors that have no exponent illustrated are understood to have a 1 as the exponent because after all we have one factor of that particular item. Well anyway, let's see, we have 10 squared. That means 2 factors of 10. 10 times 10, oh that's 100. And then here we have 10 cubed, which means 3 factors of 10. Multiplying we would get 1,000. Here we have 4 factors of 10 because this is 10 to the 4th power. And then multiplying we get 10,000. Now the important thing to notice here in the pattern is that the exponent corresponds to the number of zeros that follow a 1 in the answer. So when we raise 10 to an exponent, we get 1 followed by the number of zeros corresponding with that exponent. All right, so that means then if we're going to raise 10 to the 5th power, rather than write these 5 factors of 10, we can just say, well, this is going to be 1 followed by 5 zeros. Just a fast way to deal with that situation. When you're evaluating expressions involving bases and exponents and so forth, the safe thing to do is to expand according to the meaning of the exponents that you have involved in the problem. This says 2 to the third power, or 2 cubed. It means we have 3 factors of 2. So write down those 3 factors. This says we have 6 squared, or 2 factors of 6. Write those 2 factors down and then multiply according to the way that you understand multiplication. 2 times 2 times 2, 8. 6 times 6, 36. Multiplying here, we get 288. When the numbers get pretty big, a calculator can be helpful. Here we have 7 to the 4th power, which means we have 4 factors of 7. And we could string them out like this and multiply them if we'd like. Or a faster way is to use a calculator to make the calculation. And calculators, different kinds of calculators use different kinds of sequences or different looks for the buttons in this process. In both ideas though, with both ideas, you enter the base of the exponent and then you follow that by some key on the calculator and then follow that by the exponent and then press the equal sign or enter. Now on some calculators, that button for using the exponent notion is y to the x. On other calculators, namely graphing calculators, it kind of looks like an up arrow head, kind of like this. So it's 7, and then this button says enter the exponent. You enter that exponent, then press enter, and we get our answer. It turns out to be 2,401. Here's another one, 10 to the 7th power. Remember what we talked about a moment ago. If we're raising 10 to some exponent, then the answer is just a 1 followed by the number, followed by 0, the digit 0 used this many times. So it's 1 followed by 7 zeros. And it's 10 million. What is the square of 7? The square of 7 means 7 squared. It means 2 factors of 7. The safe thing to do, rather than, now when you look at this, you might think, oh, 7 squared, okay, that's 49. And you could write 49 and that's a safe answer and it's the correct answer. But the safest way to do this, especially when you first start dealing with exponents, is to write the 2 factors of 7 indicated with this notation and then come to an answer. Suppose we want to evaluate x squared y cubed when x is 5 and y is 4. Well, let's see. We write down our expression to begin with, then we replace letters with numbers. X is 5, so this is 5 squared. Y is 4, so this is 4 cubed. Notice that we write the expression, and in the first step we replace letters with numbers and we do no evaluating. That is, we don't multiply, divide, subtract anything. We don't do any operations in this first step. We're just replacing letters with numbers. That's it. All right, now we kind of go through the process. And we're thinking, well, exponents are involved, so let's indicate what we have here in terms of factors. This is 2 factors of 5, write them down. This is 3 factors of 4, write them down. And now we begin to multiply. 5 times 5, 25. 4 times 4 is 16, and I'll bring down this other 4. I'm trying to be safe here and just do 2 items at a time, or deal with 2 factors at a time. Now I'm noticing an opportunity, and that's why I've kind of stopped right here. We could, and the indication is to multiply 4 times 16 and get a result here and multiply that by 25, and that would be just fine. Or we can think, wait a second, I'm seeing an opportunity here of 4 times 25. You see, this is just a string of 3 factors, and we can multiply any 2 of them first. Our commutative and associative properties allow us to do that, because after all, our commutative property would allow us to swap the order of these 2, and our associative property would then allow us to associate 25 with 4. And the advantage of that is that 25 times 4 is 100. So we could have 25 times 4 is 100, and then times 16, and that's just 1,600. And we know the shortcut in multiplying by 100 or 1,000 or 10 is just to multiply 1 times this rascal, whatever it is over here, and then followed by the number of zeros we have. If this was 1,000, we'd have 3 zeros, and so on. So 1,600 here. Now we don't always have to show the use of the commutative and associative properties here. We know that they exist, and so we can just think, well, with those properties, we can multiply any two of these factors first, and we're choosing to multiply those two first because it makes the problem so much easier. Here's a situation where we want to take this expression and kind of consolidate it using exponents. Now, all we're doing is looking for the multiple use of the particular factors that are involved. We see a string of factors. We see that 6 is used as a factor 1, 2, 3 times. So this is 6 to the third power, or 6 cubed. I have x here, 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 and here. I have 4 factors of x, so this is x to the 4th power. And then I have y 1, 2 times as a factor, so that's y squared. So we can rewrite this using exponents as 6 cubed x to the 4th y squared. We discovered earlier that subtraction is related to addition. And now we're going to find, and it should be no surprise, that division is related to multiplication. Consider this situation. In 6 times 2 equals 12, we know that 6 and 2 are called factors of 12. They are the items being multiplied to get 12. Perhaps it's no surprise that 6 and 2 are also called divisors of 12. After all, they will go into 12 a whole number of times. And in fact, 6 goes into 12 2 times, and 2 goes into 12 6 times. And it's because of this multiplication idea that we have that even division idea. So that relationship is intertwined here. Now, division can be illustrated in a lot of ways. One way is like this: 12 divided by 6 is equal to 2. Another way is to perform this operation of division using long division. And the way we use long division, as you recall, is like this. 6 into 12 goes 2. 2 times 6 is 12. The remainder is 0. Now, the 6 is the divisor. The 12, the number we're dividing into, is called the dividend. And the answer in the process is called the quotient. Now, notice that in this process, when we actually first start, when we have this situation where we have 6 into 12, we're kind of saying to ourselves, what times 6 is equal to 12? And once we get an answer, we are understanding that it's the quotient times the divisor that gives this dividend. And it is that then becomes the reason that this is the correct answer. That is, 12 divided by 6, and by the way, this is another way to show division. 12 over 6 means 12 divided by 6 is equal to 2 because 6 times 2 is 12. You see, because 6 times 2 is 12. And let's extend the idea farther. I've repeated that step over here. 12 divided by 6 is 2 because the divisor times the quotient and divisor are multiplied to give the dividend. And if that's true, then this is the correct answer you see in the division problem. Now, using the same idea, let's talk about ones and zeros here a little bit. 5 divided by 5 is 1. The reason we know that is because when we multiply the divisor and the dividend, the divisor and the quotient, we get the dividend, you see. So it's because 5 times 1 is equal to 5. And 5 divided by 1 is equal to 5 because, once again, 1 times 5 is equal to 5. Now, we can extend this idea more generally that if we have just any whole number except 0, any whole number but 0 divided by itself is going to be equal to 1 because of this same idea. And any whole number but 0 divided by 1 is equal to that same number. A over 1 is equal to A because 1 times A is equal to A. You see, that's the idea. Now, the situation with 0 is rather unique. These are very different ideas from one another, but we can evaluate the situation using the notion that this means long division. Let's have a look at this.
Let's look at the difference between 0 over 3 as a fraction and 3 over 0. Now, we know that a fraction implies a division problem. In this one, it means 0 divided by 3. So as a long division problem, it's 3 into 0. Now, what's the nature of long division? It means that we're looking for a number that we call the quotient, which when multiplied times the divisor gives the dividend. In other words, what number times 3 is equal to 0? And we can answer that question with a number, and that number is 0. Now that's why 0 over 3 is equal to 0. But look at 3 over 0. That means 3 divided by 0, or 0 into 3. Again, we're looking for a number which when multiplied times the divisor gives the dividend. In other words, what number times 0 is equal to 3? Well, no number times 0 will be equal to 3. And that's why 3 over 0 is undefined. And anytime we have a fraction with a 0 denominator, the situation is undefined.
Let's run through the long division process. If we're dividing 4 into 3,192, we might reason like this. We might think, well, 4 doesn't go into 3, but we'll think of 4 into 31. 4 into 31 goes 7 times. 7 times 4 is 28. Now, we identify it as 7 times 4 to be 28 because we're looking for the most number of times that 4 will go into 31. The most number of times that it goes into 31 is 7. That is, 28 is the largest multiple of 4 that is below 31. That's another way to look at it. At any rate, we go through like this. 7 times 4, 28, then we draw a line and subtract. 28 from 31 we find to be 3. And we bring down the next digit and away we go again. 4 into 39. Let's see, 4 into 39, gee, it doesn't go evenly. I'm thinking about the largest multiple of 4 that is less than 39. That's a way to think about it. But I can kind of reason like this. I'm thinking, well, gee, if this were 40, then 4 into 40 would go 10. See, so it doesn't go 10 times. Let's try 9. You see, that's a way to reason through on this particular problem. 9 times 4 is 36. And then draw the line and subtract to get 3, bring down the next digit, and away we go again. 4 into 32 goes 8. 8 times 4 is 32. We draw the line, subtract, and get a remainder of 0. So when the remainder is 0, we say that 4 goes into this number, 3,192, evenly, a whole number of times, and that number is 798. We could check our work by verifying that 798 times 4 is indeed 3,192. Let's try a 2-digit number. 14 into 301. We reason this way. We think, well, we think of 14 into 3. No, we can't divide 14 into 3. 3 is not large enough. 14 into 30 goes 2 times. 2 times 14 is 28. Draw the line and subtract. 8 from 10 won't go. We borrow from the 3. And we can probably see this very easily. 30 minus 28 is 2. But if we're taking this kind of digit by digit, we would think 8 from 0 won't go. Borrow from the 3. The 3 becomes a 2. And this becomes a 10. 10 minus 8 is 2. You see, that's another way to think about it. Now we bring down the next digit. It's 21. 14 into 21 goes 1 time. 1 times 14 is 14. We subtract and get 7 as our remainder. Now, there are a couple of ways to show the answer in this problem. One, I think, a very accepted way is to say 14 goes into 301 21 times with a remainder of 7. You see, with a R, remainder of 7. Illustrating the remainder here like this is perfectly all right. Another way, and a rather algebraic kind of way to do that, would be like this, or to show the remainder is like this. It's 21, the answer is 21, plus the remainder over the divisor. You see, and really this is just 1/2 when we reduce the fraction, so this is 21 and 1/2, so 21 and 1/2. We say that 14 goes into this number 21 and 1/2 times. You see, this is a complete answer, but that's a complete answer as well. Now, this answer is rather interesting because it leads us to a way of checking the situation. And here's how we go through the check. We take our quotient, multiply times the divisor. Now the whole numbered part of the quotient is 21. 21 times 14, what do we get? Well, I did that over here. 21 times 14, we get 294. And then we add our remainder, you see, of 7, and lo and behold, we get the 301 here that we expected. Okay, so that's the way to check it. Couple of words and word phrases lead to the notion of division. I guess it's kind of obvious. The quotient of. Quotient is the answer in a division problem, so the word quotient leads us to a division problem. Now, the important thing is to set the problem up correctly, to divide which number into which correctly. The quotient of one number and another means we're taking this number and dividing by that one. You see, that last number is the divisor. So this is 15 divided by 3. And here it is in words, 15 divided by 3. Divided by implies the idea of dividing as well. Evaluate x over y when x is this number and y is 18. Now, x over y means x divided by y. So that's all we're doing here is going through the division. I'll go through the evaluation over here. Now, remember, we write down the expression being evaluated. We replace letters with numbers. Now, x is replaced then with 4,284. Y is replaced with 18. Now, it is a fraction. It is an implied division problem. So we can leave this area, we can kind of come out to the side of this and perform that indicated operation. And that indicated operation is division. 18 is the divisor. The dividend is 4,284. And away we go with our process. Let's see, 18 into 48, perhaps 2 times. 2 times 18 is 36. Subtracting, I get 6. Bring down the next digit, 8. 18 into 68, maybe 3 times. 3 times 8 is 24. I'm carrying 2. 3 times 1 is 3 and 2, 5. 54, I subtract here. 8 minus 4 is 4. 6 minus 5 is 1. Bring down the next digit, 4. I suspect that this is probably going to be about 9 maybe. 9 times 8 is 72. Carry 7. 9 times 1 is 9 and 7 is 16. That's too much. See, now this becomes a study in trial and error when you go through this, and I'm sure you know that from past experience. All right, well, let's see. I've got 18, perhaps it goes 8 times. Let's see. 8 times 8 is 64, carry 6. 8 times 1 is 8 and 6, 14. Oh, happy day. It goes evenly because the remainder is 0. So the quotient here that we're looking for, evaluating here, we find this to be, by this long division process, 238. Next problem. Is 28 a solution of this equation? Well, to determine whether or not we have a solution, we want to determine whether or not the value given for the letter makes the statement of equality true. So all we do is this, and I'm kind of jammed with space down below here, so I'm going to come out to the side to answer the question. Now, we're trying to find out if 28 is a solution to this equation. If it is, it's a replacement for x that causes this statement to be true. So to show that it is a solution, and it turns out to be one, we replace x with 28, and we illustrate that we have a true statement. 28 divided by 7 is 4. 4 is equal to 4, a true statement, therefore 28 is a solution. We mentioned earlier that divisors and factors are related to one another, and let's talk about that just a little bit more because we're going to extend that notion into some other ideas. If 12 times 1 is 12, then these two numbers are multiplied to give 12, so these are factors of 12. 6 times 2 is 12, so these are factors of 12. 4 times 3 is 12, these are factors of 12. If I want to list the factors of 12 in order, then I would list this. I would say the factors of 12 are 1, 2, 3, 4, 6, and 12. Now let's think about divisors. 4 goes into 12 3 times because 3 times 4 is 12. So 4 is a divisor of 12. 3 is also a divisor of 12 because the division goes evenly. 6 goes into 12 evenly and is a divisor. 2 goes into 12 evenly and is a divisor. 12 goes into 12, 1 goes into 12. So these are all divisors of 12. If I list the divisors of 12, they are 1, 2, 3, 4, 6, and 12. The important idea is that these two lists are the same And so factors and divisors are pretty much interchangeable. Kind of depends on how we're sort of looking at the situation. If we're dividing, we think of divisors, and if we're multiplying, we think of factors. But it does turn out that if